Hi, welcome to the first video of a series of videos where I will try to explain and teach everything related to every problem from the ACT test. Um, I hope this can help anyone there needing to understand why the answers are what they are, and also that this knowledge can help them solve new problems that are different in the way they have been written, but that in the end the maths are the same. So, welcome. So, this is the first problem from the math section. Um, it's asking you to calculate a probability, and we will try to understand why the solution is what it is. So, if you haven't tried, I would recommend you to try it. And once you have tried, you can so pause the video, try it, and once you have the solution, you can come back here. Okay, let's begin. So the question is saying that uh, in different pieces of paper, numbers were written from 1 to 15, each number for each paper, and then these pieces of paper were put in a jar. Then randomly, and by randomly it means that people doesn't know what number they are about to draw. So in this case, they are asking what are the chances of this paper being any of the numbers from 1 to 8. 9 is not included because if it was included, it would say less than or equal than 9. So that's the reason. Okay, first of all, let's try just trying to understand what's happening. There is this jar where people will put different pieces of paper, and each of them will have numbers from 1 to 15. Now, um, so we have many ways to understand what's happening here. The first, like, key idea to understand is going to the meaning of probability. That alone can give you a lot of information. So probability is basically telling what's the proportion of something that you wish it would happen divided by the totality of options that could happen. So let's write here totality, and here it's a part of the totality. What do I mean by this? If you were to draw one piece of paper, you could have numbers. You could either have a 1 or 2, a 3, a 4, a 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, or 15. So all of these numbers represent all of the options. So this is the totality. But what happens if we decide to understand how often I would get, for example, this subset of numbers? So that means that what I call the part of the totality only means that the piece of paper would have either a 5, a 6, or a 7. So we can now understand that the proportion of events that I wish that they would happen compared to the whole amount of events that could happen, that would give me the probability that I am looking for. So in this case, for example, the number of events that under this, the number of events where the piece of paper has either of these numbers is only 3, but in this case, the number of events is 15. That's why in this case, we would get 3 divided by 15. So that would be the probability of getting 5, 6, or 7. Okay, once we know this, we can come back. We can now try to get the answer for the case of the statement we are trying to answer. So the statement says that any number that is less than 9. So that means 1 to 8 are the possible events that we wish to analyze. So because we have numbers from 1 to 8, that means the number of events corresponding to the part of the totality are 8, and the totality is still 15. So that's why, in this case, the answer would be 8 over 15. So if we come back to the statement of the problem, we see that this is then the answer, 8 over 15. Now, if we want some variations to this problem, we could also think like, what would be the probability of, let's say, drawing a piece of paper and this piece of paper having the odd numbers. Remember that an odd number is any number that can be written in this way, where n is an integer. So all odd numbers then could be expressed by 1, 3, 5, 7, 9, because we can see that 1 is whenever n is equal to 0, 3 is whenever n equals to 1, 5 is whenever n equals to 2, and so on and so forth. So in this case, we want to consider, in this case, that we have all those numbers up to 15. So which of these numbers and how many of them are odd numbers? We can see that 1, 3, 5, 7, 9, 11, 13, and 15 are odd numbers. So these are 8 numbers. So in this case, the probability would be 8 divided by 15. And we can also ask the same question for what's the probability of drawing a piece of paper with an even number, which in that case, because we know that these numbers are 15 and the odd numbers are 8, the even numbers should be the remaining from 15. That is 7 numbers. And these numbers, in case you don't remember, are all those numbers that can be divided by 2 and you still get an integer. And these are the 7 numbers. So in this case, this would be the prob. It's an interesting observation of this is that because this here, this part of the totality, and this other part of the totality that is completely independent, you can see that their sum is actually equal to 1, because it's the sum of these two parts of the totality that brings you back to that totality. And this is a special property of the probability. Okay, now we can think in another kind of variation of this problem. We can now think what would be the probability of getting a single number, let's say 3. What's the probability? Well, because you know there is only one piece of paper with 3, that means you only have one event and you still have 15 events, 15 different possibilities. What would happen if someone to the pieces of paper from 1 to 15, and if someone secretly would have added the following numbers? So then each of the numbers have a different frequency. So this person added 10 more numbers. So what's the first thing to do here? let's try finding again how many different possibilities we have. So in this case, we have 25 different pieces of paper. By different is just the fact that there are different pieces of paper. Even though they could have the same number, in the end you have 25 pieces of paper. Okay, but now when we wish to explore a probability, and let's imagine that we are now interested in studying the probability of the following. Again, if the piece of paper was the 3, the number written on it, in this case, because all of these new numbers, none of them is a 3, we still only have one 3. So that's the amount of the part of the totality, but down here we now have a change. Instead of 15, we have 25. And, and what about the probability of getting a 7? Because in this case, we have now added 3 more 7s to the one that was already here. That means that we have 4 7s right now. And again, the totality is 25. And a more advanced question to this situation could be, what's the probability of first drawing a piece of paper with the number 3 written on it, returning it to the jar, and then drawing a second piece of paper with the number 7? So we have these two numbers, and because we are returning the first piece of paper, the totality will remain the same for the second number. To understand how to calculate this, it's important to first analyze a simpler scenario. We will come back to this. Let's imagine we have a coin, and the coin has a tail or head. And here we would, a similar question as the previous one would be, what's the probability of tossing the coin once, getting a tail, and then tossing again the coin and getting a second tail? So we are trying to find this probability of this event. Now, if we were to study the totality of events for tossing twice the coin, how we would do that? So we can see that we either, as a first event, we have either a tail or a head. But then we can also see that for the second event, after already having a tail, for example, we could also have, again, a tail. Or for the first event where we had a tail, the second one could be a head. On the other hand, if the first event was a head, the second event could also be a head. Or if the first event had been a head, the second event could have been a tail. And this is all possibilities for tossing the coin twice. So the totality here is 4. So we can now count how many events are the ones we are interested, and we see that there is only one case where the two tossings provided us a tail. That's why this is a 1. And the probability of having two tails, it's then 1/4. So we can now come back here and we can ask the question, if, because it will be hard once we start having more, because it gets hard every time the possibilities start increasing. Let's say once we have like a dice where instead of having only 2 possibilities like here, we have 6, counting becomes harder. That's why something that can help us is understanding that because each tossing here, for example, was an independent event, then this one could have been calculated in a much simpler way. we could just have calculated the probability of getting a tail times the probability of getting a tail. And because the two of them are 1/2, we also get 1/4. So we can come back to this problem and now see that we also have a similar situation here. And this one would be this, because there are 4 sevens, just like we computed them here, times 1 over 25. Sorry, this should be a 25. So we get this as our final answer. You can see here how cumbersome it would have been to calculate this amount of probabilities. Sorry, to have calculated this amount of events. This is a very big number. As a last exercise that I want to leave to you uh, would be, what if we want to toss the coin 3 times, and now we want the probability of getting 3 heads. Could you do that? I hope this explanation has helped you. Please, if you have any questions, you can just leave the comment and I will try to help as much as I can. Also, I will very soon add to the description a link with some notes where new problems can be found, and also the explanations to the solutions are there. I hope this can help, and please, I'm here to help.